So dear students, I welcome you for the today's lecture related to the Bode Plot Numerical. So this is the next example, that is the transfer function is given, which is k upon 10s plus 1 into again 10s plus 1, that is nothing but 10s plus 1 whole square, where tau that is having the value of 10. So we can split this into the two transfer functions, that is gs1 and gs2. So gs1 that becomes 1 upon 10s plus 1, and similarly g2s that is also 1 upon 10s plus 1. Now our amplitude ratio for first order transfer function, that is nothing but 1 upon under root of 1 plus tau omega whole square. So this can be written as the amplitude ratio for the first transfer function, that is 1 upon under root of 1 plus tau omega square, that is tau is 10 omega into 10 omega, that is 10 omega square. So similarly, amplitude ratio for the second transfer function, that will be same as 1 upon under root of 1 plus 10 omega square. So overall amplitude ratio, that is the addition, that is the multiplication of the two amplitude ratios. So amplitude ratio 1 into amplitude ratio 2, that will be equals to the overall amplitude ratio. However, when it's a question of phase angle, the phase angle, that is the overall phase angle, that is nothing but the addition of the phase angles. So this is the phase angle, overall phase angle, that is nothing but the phase angle 1, phase angle 2, phase angle 3. So in case of the overall phase angle, it's the addition of the phase angle. However, in case of the transfer amplitude ratio, it's the overall amplitude ratio, that is nothing but the multiplication of the individual transfer function amplitude ratio. So overall amplitude ratio, that is the multiplication of amplitude ratio of first transfer function into the second transfer function. So taking out the under root, you will get the overall amplitude ratio, which is equal to 1 upon 1 plus 10 omega whole square. Now first thing is that the low frequency asymptote, which is omega tends to 0. So I am going to substitute this omega tends to 0. That means I will be remaining with 1 plus 0, that is nothing but 1 upon 1, that is amplitude ratio, which is equal to the 1. This is a low frequency asymptote. So I am going to plot this amplitude ratio against the omega frequency W. So this amplitude ratio, which is equal to the 1, I am going to plot it here, so that amplitude ratio, which is equals to the 1, amplitude ratio upon Kc, which is equals to 1, and for omega I am going to plot a straight line here. This is the low frequency asymptote. Then for high frequency asymptote, I am going to substitute omega, which tends to infinity. That means omega will have the higher values. Higher values means omega will have the value of 10, 100, 1000, 10,000 and so on. So if I am going to substitute this in this equation, AR upon Kc, which is equal to 1 upon 1 plus 10 omega whole square. So it becomes equal to the 10 omega into 10 omega, that is 1 upon, sorry, it will be 1 upon 10 omega whole square. So this is the amplitude ratio that will become equals to log of amplitude ratio, that is equals to minus 2 log of 10 omega. Now it's a y is equal to mx plus c. Now this is the x is nothing but the amplitude radian frequency omega, and y is nothing but the amplitude ratio. So m is now minus 2. M is now minus 2 for this case. So the slope, that is minus 2. Slope is minus 2. So it's a straight line passing with a slope minus 2, and the equation of line passing through amplitude ratio upon Kc, which is equal to 1. Now this 10 omega, which is equal to the 1, that is nothing but the tau omega. This is tau omega, which is equals to the 1. That is going to give the omega which is equal to 0.1, and which is nothing but the corner frequency W dash. So the point of intersection of low frequency asymptote and the high frequency asymptote is calculated by substituting the tau omega, which is equals to the 1. So omega I can calculate as 0.1. So at this 0.1, the point of intersection of the low frequency asymptote, this is the low frequency asymptote, and the point of intersection of 0.1, I will draw a second line with the slope of minus 2, with a slope of minus 2. This is the slope of minus 2, and will intersect the low frequency asymptote and this high frequency asymptote. They will intersect at point of 0.1. So this is the one of the simplest problems. Now in this case, I have done some points as bold. So this is nothing but the tau values. Every time you are doing with the same things. That is, you are writing the transfer function, separating the 2 or 3 transfer functions. Then write the G1s as one of the transfer functions. Then amplitude ratio, which is if the first order system, then the amplitude ratio is 1 upon under root of 1 plus omega tau square, where omega and tau that is going to be replaced for that particular transfer function. Tau will correspond to that particular transfer function. Then the low frequency asymptote, that is omega tends to 0. I am going to substitute these values in this amplitude ratio and simplify that. Mostly it comes as amplitude ratio, which is Kc equals to 1. So this is the equation of line passing through amplitude ratio upon Kc, which is equal to the 1. This is overall written here because both are clubbed at this point. Then the high frequency asymptote, omega tends to infinity. So omega value that will exist in this case of high frequency asymptote, writing it in terms of the log values, so it becomes slope of minus 2. And amplitude ratio, which is equal to the 1, and this tau omega, which is equals to the 1. So I can calculate the omega value, which is nothing but the corner frequency. Now next is the phase angle. Phase angle, our formula is theta, which is equal to tan inverse of minus omega tau. So for this case, the 2 tan inverse of 5 omega, that will be there. Now substituting one by one values, omega which is equal to 0, omega which is equal to 0.1, omega which is equal to infinity. Now in this case I can take 0.1, 1, all the values that can be taken. Why a 0.1 that is taken? Because my corner frequency is 0.1 in this numerical. So I am taking this omega which is equals to the 0.1. I can take 0.01, I can take 1, I can take 10, 100. So subsequent values are to be used for this omega and can be substituted in this equation, and the phase angle theta that can be calculated, which is nothing but 2 tan inverse of 5 omega. So that comes 0, minus 90 and minus 180. So from 0, minus 90, 180, minus 180, that is plotted, and with a phase angle, with the omega at 0, phase angle is also 0. With omega, this is what the omega values, omega tends to 0, the phase angle is also 0. And if the omega, that is infinity, the phase angle is minus 180. So I will get these 2 points. That is, first is omega which is equal to 0, the phase angle is 0. I will get this point. Then second point, 0.1 omega and with minus 90. 0.1 omega, 0.1 omega with a minus 90 value, second point. And the third point, that is minus infinity and minus 180, I will get the third point. Intermittently, I can calculate also omega which is equal to the 1. Omega which is equals to the 1. The theta that can be calculated, that comes approximately equals to this, say 135 or so, whatever it is. So depending on this intermittent values, I will get the nature of the curve, something like this. The next is this, again, simple transfer function. Here nothing is there in the denominator, everything is in the numerator. That is what, kc into 5s plus 1 whole square. So again, the two transfer function, g1s, first transfer function is 5s plus 1. The second transfer function is same as 5s plus 1. So writing the amplitude ratio, in this case the amplitude ratio is only under root of 1 plus 5 omega square, under root of 1 plus 5 omega square. So similarly, amplitude ratio 2, that is also equals to the 1 plus under root of 1 plus 5 omega square. So overall amplitude ratio, that is AR into Kc, which is equal to the under root of 1 plus 5 omega square into under root of 1 plus 5 omega square. So this can be simplified as 1 plus 5 omega square. Then the low frequency asymptote, which is omega tends to 0. So omega tends to 0, this will go in when, and only AR upon Kc, that comes as the 1. So this is the equation of line passing through amplitude ratio AR upon Kc, which is equal to 1. So I am going to substitute this AR upon Kc, which is equals to the 1. I will draw this low frequency asymptote value. The next is high frequency asymptote value. Omega tends towards the infinity. Substituting this omega tends to infinity, that comes as the 5 omega whole square. So AR upon Kc, which is equal to 5 omega whole square. So that is nothing but, it is nothing but 5 5 omega whole square. So taking log of this, log of amplitude ratio upon Kc, which is equal to 2 log of 5 omega. So again, the y is equal to mx plus c, that comes as the 2 is the slope and the 5 amplitude ratio, which is equals to 1, 5 omega, that also comes as the 1. So 5 omega, which is equal to 1. So the omega, which is equal to 0.2. So omega 0.2 is nothing but the corner frequency. So from point 0.2, I will have the high frequency asymptote with a slope of plus 2. Plus 2, that means it will move upward direction. The next is the phase angle. So phase angle is our theta, which is tan inverse of omega tau. So 2 tan of 5 omega. So omega, which is equal to 0, omega, which is equal to 0.2, as the corner frequency is 0.2. So I am going to put omega, which is equal to 0.2, and third is omega, which is equal to infinity. And calculating the phase angle, that comes as the 0, 90 and 180. So I can plot all these three phase angles at a point 2. I will get a value of 90 now in this case. For this phase angle omega, which is equal to 0.2, the value of theta phase angle, which comes as the 90. And the rest of the two values are there. So I can have the curvature like this. Now next is the transportation lag. In this transportation lag, it is yt, which is equal to x into bracket t minus tau d. So the transfer function is gs, which is equal to e raised to minus tau ds. So substituting s, which is equal to the j omega, and converting it into the complex function, therefore the amplitude ratio is nothing but the modulus or absolute values of g of j omega. So taking the modulus of g of j omega, that is going to give you the e raised to minus tau dj omega, which is equal to the 1. And the phase angle, which is theta, which is equal to minus tau d upon tau dw. So this phase angle characteristics for transportation lag parameter is obtained by the phase angle versus omega tau d, and the theta is our given as the angle. Now if you will draw the amplitude ratio, which is equals to the 1. So it will be a straight line with a amplitude ratio omega, which is equal to the 1. So your graph will be a straight line in this case. Then this is the what derivation that is given, and if we will plot omega theta, which is equal to minus tau d omega, so that behavior is like this: theta is equal to omega tau d, all the angles which comes as minus 45, 90 and so on. So it goes on decreasing. So this is for the transportation lag functions. Now next numerical, that is the gs, which is equal to the kc s upon s plus 1 into 0.1 s plus 1. So there are three transfer functions. One is the s, second is the s plus 1, The third is the 0.1 s plus 1. So one by one we will consider, we will draw the individual lines. So G1s, which is nothing but the S. So AR amplitude ratio 1, which is equal to the omega. Tau is only 1 in this case, tau s. So omega s, which is equal to the 1. So log of AR1, which is equal to the log of omega. So this is the value amplitude ratio. So this is the equation of line passing through amplitude ratio, which is equal to 1, and omega, which is equal to the 1. So this is what the first line that can be drawn. So slope of plus 1 that will be there. A slope of plus 1 that is there. So it's a line passing through the origin. 0, 0, 0.01, 0.01. So this line passing through the origin, it will be the asymptote for the first transfer function. Then the next is 0.1 s plus 1. The transfer function is 1 upon s plus 1. So this is my second transfer function. So for this, tau is which is equals to the 1. So my amplitude ratio, which is nothing but 1 upon under root of 1 plus tau omega square, which is tau is 1. So it is simply omega square. So low frequency asymptote, omega tends to 0. I am going to substitute here 0. So remaining will be only under root of 1. So 1 upon under root of 1, that is nothing but the 1. So this is the equation of line passing through amplitude ratio 2, which is equal to the 1. So amplitude ratio, which is equal to the 1, low frequency asymptote. The next is the high frequency asymptote, where omega tends to infinity. So amplitude ratio, which is 1 upon under root of 1 plus omega square. So 1 will be neglected. It will be under root of omega square. So under root of omega square is nothing but the omega. So 1 upon omega, that will be there. So log of amplitude ratio 2, which is minus log of omega. So minus 1 is the slope for this case. Minus 1 is the slope. So amplitude ratio 2, which is equal to 1, and this omega, tau omega, which is also equals to the 1. So in this case, the corner frequency W2, that comes as the 1. So this corner frequency that comes as the 1, and with a slope of minus 1, that line will be there. So from this point 1, the slope of minus 1, I will draw the another line. So this line is for the transfer function of s plus 1, 1 upon s plus 1. Then the third transfer function. So the third transfer function is 1 upon 0.1 s plus 1. That is amplitude ratio 1, which is equal to 1 upon root of 1 plus tau omega whole square, that is 0.1 omega whole square. So low frequency asymptote, omega which tends to 0. Amplitude ratio 3, that comes as the 1. So it is the equation of line passing through the 1. So I am going to draw this low frequency asymptote again here. Now plotting the high frequency asymptote, omega tends to infinity. So omega, this term will be there, 0.1 omega whole square. So taking out the under root, it becomes 0.1 omega. So I will take a log of this minus log of 0.1 omega. So slope will be -1, slope is -1. Then this 0.1 omega, which is nothing but equals to the 1, to calculate the corner frequency. So omega, that comes as the 10. So corner frequency is the 10. W3 corner frequency is 10. So from this value of corner frequency of the 10, I will start with the high frequency asymptote with a slope of -1. So it is a slope of -1. This high frequency asymptote will start here. So this is the high frequency asymptote for the third transfer function, high frequency asymptote for the second transfer function, low frequency asymptote for the second and third transfer function, and this is the for the first transfer function. Now the overall amplitude ratio, that is nothing but the log of amplitude ratio 1 into log of amplitude ratio 2 into log of amplitude ratio 3. The next is the phase angle. So phase angle, which is nothing but the phase angle 1 plus phase angle 2 plus phase angle 3. So in this case, tan infinity plus tan inverse of minus omega plus tan inverse of minus omega, 0.1 omega. So tan infinity, that is nothing but 90, then tan minus omega and tan minus 0.1 omega. Because our formula is theta, which is equal to tan inverse of minus omega tau. So this is tan of minus omega and tan of minus 0.1 omega. So the phase angle, which is equal to the 2, phase angle for the 1, it's a 90. So we can draw a phase angle which is nothing but the 90 plus 90 for the first transfer function. This is for the first transfer function G1s, which is the transfer function is only S. The next transfer function is tan inverse of minus omega, it's the theta value. So substituting the phase angle to or calculating tan inverse of minus omega, this is nothing but tan inverse. So omega, which is equal to 0, phase angle 2, that becomes equals to 0. Substituting omega, which is equal to 1, phase angle is minus 45. Omega, which is equal to 10, phase angle is minus 85. Omega, which is equal to infinity, phase angle is minus 90. So the phase angle for the 2, that is for omega, which is equals to the 1, omega, which is equals to the 1, the phase angle is 45, this line. Then for 10 value, the phase angle is minus 85, and then the next is it goes towards the infinity. Next is for the third transfer function, that is tan inverse of minus 0.1 omega. So substituting the value of omega as 0, 0.1, then corner frequency of 2. So here I have to take the 0.1 omega, which is equal to 0, 0.1 omega, which is equal to 1, 0.1 omega, which is equal to 20, 0.1 omega, which is equal to the infinity. So phase angle third is 0, minus 45, minus 87, and minus 90. So this will be the line for the third transfer function. Then what will be the overall transfer function? There is the first transfer function, which is a steady line at 90. So I have to add all these this plus 90 minus 45 and again minus 45. So adding all these value, I will be drawing this resultant overall phase angle.